So this box right here, what section of that is shaded? 1/4, huh? 1/4. Now, what section of B is shaded? Yeah, it looks like there's 8 pieces there, right? 1, 2, 3, 4, 5, 6, 7, 8. And 2 out of 8 are shaded. And you know 2 out of 8 is the same as 1 out of 4. And you can see it by those diagrams readily, right? As soon as you look at them, you say that's the same portion that's shaded. So this is just a nice way to demonstrate what you already know, what kids won't know at first, that 2/8 and 1/4 are the same, aren't they? And so that's a good way, because remember, you always want to be showing them that math is just simply truth. It's not just a bunch of rules, because that's the tendency of kids, is to think math is just a bunch of rules. We just got to memorize all the rules. But rather, if you're showing things like these pictures, then you're showing, oh yeah, those really are the same, aren't they? And so the rule, which you guys know, right, dividing top and bottom by 2, the reduction rule, is actually a rule that's true. It's just leading us to what's true. How about part C? What do they want me to do on part C? What? How many squares we got there? Yeah, it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 3 out of 12 are shaded. How about the last one? 4 out of 16. And those are all the same. You could reduce any of those fractions. I'm not really into the names. I promise I will not ask you for one of those names on the test. I actually got it wrong before class, and I've done this actual lecture before. I was looking at it, and in fact, here, I'll move it up to there. So for each of the following, write 3 fractions. Yeah, okay. So they want us to take, so coming down here to part A, they want us to take 5/6 and make it something over 30, where it's really still the same, equal, right? Because we got that equal sign right there. So 5/6 is equal to what over 30?
25.
Yeah. And so how would you teach kids to do that? Like, what do they have to actually do to the 5/6? Yeah, top and bottom by 5, huh? So that would become 25/30ths, like that. So that's getting them ready for the idea of common denominator, right? When we do the top and bottom of a fraction by the same thing, this fraction is the same as that fraction. Or you could say it's just the opposite of the reduction we just did. And a minute ago, back over here, we said these are the same because you could reduce, right? Divide top and bottom by 2 and you get that one. Now I'm multiplying top and bottom by 2, or 5. Just the opposite, right? So this fraction's the same. How about over 48? What if you wanted to change 5/6, you want to make the denominator 48? What would you do top and bottom there? Yeah, whatever it takes would be, 8, huh? 8 on that one. So that'd be 40 over 48 is the same, and on you go. Maybe we could go to part C. What do they have to do for C or D? Okay, part C, 0 over 12 is what over 60?
0.
Yeah, and 0 over 12 is what over 96?
0.
And 0 over 12 is 0 over 108. Does that make sense? Because it doesn't matter what you multiply top and bottom by. If the top's multiplied by 0, it's just going to be 0. So 0 in the top of a fraction is always just 0, isn't it? Right? If you said, last night I had 0/6 of the pie, that would be no pie at all. Right? 0/6 is just a weird way to say no pie, isn't it? So, so the number, and now, what about... Okay, so what is, on part A here, or part D, first part of D, A over 4 is what over 8?
2A.
Yeah, so I just multiply top and bottom by 2, don't I? And it's going to be 2A, exactly. So top and bottom by 2, it's going to be 2A over 8. Because 2A over 8, that can reduce to be A over 4, because 2 goes into 8 4 times, huh? How about A over 4 is what over 40?
10A.
Yeah, just multiply top and bottom by 10. You've got it. So I'll move on and solve it. So starting with part C, if you have 0 in the top of a fraction, that's just 0, as we just said, right? Last night I had 0/5 of the pie. So that means no pi. It's just a weird way to say no pi. But what about 3 over 0?
Is that undefined?
Yeah, do you know that one's actually undefined? It's not 0, it's undefined. If you have your calculator, you can divide, it'll just give you an error. Why is that? Why is 0 in the bottom undefined? Well, it's because if you tried to go into 3, you go in there infinite times. It's actually infinity. That's what it is. We just say undefined, meaning it's not a number. It's infinite. You know what I mean? Because let me show you. Let me quit saying, do you know what I mean? And show you. If 10 divided by 2, you all know the answer to that. What's the answer to that? 5, right? And why? Because 2 goes into 10 5 times. So a fraction really means how much the bottom goes into the top. That you know. So think about that with 0 on the bottom. How many times does 0 go into 3? Like if you wanted a long divide. Well, it goes in there forever. Right? You never run out of zeros in 3, right? It goes in there forever, never, never. That's why it's infinity. That's why it's undefined. That's not the same as 0 in the top. 0 in the top, that's just 0. So does that make sense, that difference? So over here then on part A, whenever they put 0 in the bottom, basically that's always going to be undefined. Because you might wonder, well, which rule works here? Because there's a 0 in the top and the bottom. Well, if it's in the bottom, that's always undefined. And so same thing here, undefined. And then as we said, part C is just 0, because there's just 0 in the top. Does that make sense on that? You can't, yeah. So 0 goes into anything an infinite amount of time. All right, so on D, 6 plus A over A. Does anybody remember their algebra rules? What's the deal there? Can we reduce that? Can we not?
It would be 6.
If we reduce it, how do we do it? Can't be reduced.
Can't you cross off the A's?
Yeah, can't we cross out the A's like
No,
that?
because addition and division aren't opposites of each other. So because the top is addition and the bottom is division, the opposite of division is multiplication, not addition.
So
It doesn't actually cancel.
Cami, you go by Cami, right?
Yeah.
Cami, I noticed on your paper. So what would work then, Cami? And you're saying, so you hear what Cami's saying? She's saying adding and dividing can't cancel each other. She's saying, right? Because dividing is not the opposite of adding. So what would go on?
So if it was 6 times A, then you could cancel the A's out.
Like that? Is that true? How could you, that sounds really good. You say it very, very clearly. How, but we, in the end, we don't want to trust in Cami or Mr. Heron or a math book. What do we want to trust in? Truth. How do we find if that's really true or not? If what Cami's saying is true or not?
Plug in a number for A.
Great. I hope, that's what I'm really encourage you to do with kids. Like when you teach them things like this, and that was excellent algebra instruction, but then to appeal to truth and just say, well, kids, let's try it out. I don't mean to call you kids, but with your students, and say, can we do that or not? Let's try it out. And just make up super easy numbers. Like how about just like 2? I just made, see, the A is, A in both places, so it's got to be the same number, right? Whatever A is, it's only one number in both places. So how about 2? That's a real easy number. Now, and what you have the kids do first off is just do what they already know is true. Like what I mean is, we know that's 8 divided by 2. All fancy math rules aside, we know that really is 8 over 2, which is really 4. So the question is it okay to cancel those 2's? Clearly not, like Cami was saying, because that makes it 6 all of a sudden. And we know it's not really 6, huh? We know it's really 8 over 2, which is really 4, so that proves it. And then Now, and then let's test Cami's other conclusion that what if we had it multiplied? What is it really now, all fancy rules aside, what is it truly? 12 over 2, which we know is 6. So we know it's really 6. So is it okay to cancel the 2's? Yeah, so what she says is true, huh? And we can all know, see how math truth is accessible for everybody. It's just about putting those numbers in and testing out those rules. Really, you can't, I was in algebra when one of my little buddies told me about it. I was confused about some rule. I wasn't getting an A in algebra, and I asked my little buddy, Mike Bell, I still remember, many, many years ago. I said, Mike, what's the rule here, da-da-da? And he said to me, Brett, just test it out, put in numbers. And it was like the first time I'd ever heard that idea. And none of my elementary school teachers told me that. That was high school algebra. And I was like, oh, wow. And I tried it, and I was like, no wonder that guy's getting an A. I never, because really there's just too many rules in math to memorize them all perfectly. There just really are. You can't be like a perfect walking encyclopedia. Instead, just test things out. just test things out. Good. Very good. So yeah, so that one cannot be simplified, huh? How about E? What's the story with E? Can we cancel them there? Because that one is multiplied down there, but that one's still added. Is it still a problem? Yeah, it's exactly right. It's still a problem. Cannot be simplified because, and it's exactly what Cami said. She stated it very well. Because dividing has to be the opposite of multiply, right? So that was 6 times A, then we could. But you can't break adding or subtracting with divide, right? Exactly. Good. And stuff. I didn't do algebra in 6th grade, but I know they do some of that now. So remember how to factor and simplify fractions? We won't be doing much of this. So does anybody remember, like, how do you, excuse me, how do you deal with this? Can I go A goes into A squared? Again, the answer is no, just like what Cami was saying, because this is a minus, and that's a minus, and we can't be dividing when there's minuses involved. So when pluses and minuses are involved, you can't be dividing things, because dividing is the opposite of multiply only, not plus and minus. So we can't do that. So then what do? We factor. You know what I mean by factor? Like you make it things multiplied. That's called factoring. To factor is to like make it multiplied. So anybody remember from algebra, what multiplies to be A squared minus B squared? Remember any of that? Are you glad that's over? You don't have to do with that anymore? Remember, A and A goes in the front. A times A is A squared. And then B and B goes in the back. B times B to be B squared. And then what signs do we need on those B's to make negative B squared? Yeah, one positive, one negative. The order doesn't matter, but one positive, one negative, how to make negative B squared. Yeah, remember that a little bit? And then how do you factor the bottom?
Take out a 5.
Yeah, remember take out what's in common kind of thing? Take out a 5 there, like that. Now it's in factored form. Now, what do we mean by factored form? We mean it's all multiplied. Do you see how it's been? See, originally, it was an A squared and a B squared subtracted, and it was a 5A and a 5B on the bottom subtracted, right? It was subtracted things top and bottom. Now, notice, it's a parenthesis, which means multiplied things. Now you might say, yeah, but there's still adding there. Yeah, but that's kind of buried though. The main structure on the top now is things multiplied, isn't it? So the overall structure in the top is now multiplied. Same thing on the bottom, it's 5 multiplied. So all the overall structures are now multiplication. So what? Well, that means exactly what Cami was saying. We can now cancel the, whoop, I just did the wrong ones, didn't I? The other one. But yeah, that's the idea, so that one stays. These two, right? Now we can cancel those two. Why? Because those are just things multiplied, aren't they? I didn't break a plus or minus, in other words. That's what's illegal, as Cami was saying. I didn't break things added or subtracted. I took that whole package. So we're left with A plus B over 5. You don't even need the parentheses on the top anymore because there's nothing to separate it from. So that's good right there. How about on part B? On part B, look at the structure right now. Right now on part B, is it things added, subtracted, or things multiplied, top and bottom on B? They're all multiplied, huh? If we had even one piece added, like if they just had like a plus 2 down there, then you could not like cancel the y's and cancel it. All that would be illegal. You might think, no, but I'm not doing the plus. Well, you are. When it's added, you can't mess with either part of the adding, subtracting. But this one's not added, right? This one has no adding, subtracting, so we can just start canceling right away. No need to do anything, but just start canceling on this one. So I'll cancel. What? 6 and 50. What goes into 6 and 50?
2.
Yeah, divide them both by 2, huh? I'll go divide by 2, divide by 2. What does that leave? That leaves 3 on the top and 25 on the bottom. And then when it comes to the letters, you just cancel, right? We have x on the bottom, x squared, that leaves 1x on the top, y squared, a single y on the bottom. There we go. So do you see that fundamental principle in when you have adding, subtracting, top and bottom? You got to factor first. You got to make it multiplied, then you can cancel. And then part B, if it's just all multiplied, you can just cancel right away. So the main thing you want to avoid is canceling added, subtracted things. You can't do that. So that's why we factor up here in part A to get around that problem. All right. Good. Little review. Equal. So like, how do you know if 13/15ths and 65 over 210, are they really equal? Are they really the same fraction? How would you know? Just reduce, huh? Yeah, just try to reduce them. So if I took this here, what goes into 65 and 210? I mean, I don't know everything, but what do you know for sure based on the 5 and the 0 that it ends in? Yeah, 5, huh? 5's got to go into both of them, huh? So if you divide by 5 and divide by 5 and you calculate, doesn't that become 13? I don't know what that is. That's not 15, is it? No. So I'll remove that arrow. So yeah, so this one becomes, what is it? 13 over 42, is that what it is? Yeah, so they're not the same, are they? They're not even close. Not equal. And so the other one, second one's the same thing. Just reduce the fractions, right? This one you would divide by 10, top and bottom, so he'd be 5, 6. This one divide by 4, top and bottom. Yeah, those are both 5, 6, aren't they? So those, part B, those are equal. Is that good? Just reduce the fractions, see if they're the same. I know I'm going quick. This will be on YouTube. There are a lot of... Okay, so the man filled his car's 8-gallon gas tank, and then he took a trip and used 1/4 of the gas. So he used 1/4 of the gas. So basically, which one of these 4 is how the gas tank's going to look after the trip, after he used 1/4? Yeah, it's B, huh? Because that's 3/4 left. Just looking at fractions on a dial. And so the man used how many gallons? Remember it started with 8? So he used 1/4 of 8. And you know what of always means in math? Times, yeah. It always means times. So that's 1/4 times 8. He used 1/4, right? He used 1/4 of his 8 gallons. 1/4 times 8. How do you multiply a fraction times a whole number? What do you do there? Yeah, put it over 1. Remember all that kind of stuff? Put it over 1. 4 goes into 8 2 times. So he used 2, which you probably just knew off the top of your head. He used 2 out of 8, 1/4 of his tank. Good. So you know all these rules, I think, and just solve for x when you got a couple of equal fractions like that.
Cross multiply.
Did you say cross multiply? Yeah, that's. There's other methods too, but I think I found that's the easiest for students. Exactly. Just go diagonal like that. You can just go diagonal, just cross multiply them. So these two. So 2 times 17, and these two, 3 times x. 2 times 17 equals 3 times x. And so let me bring it over here. So 2 times 17 is 3 times x. And 2 times 17 is, you use calculator, 34. And then what's the last step there to get x alone? Yeah, just divide by that 3, right? Divide by 3. Boom. So x is 34. X equals 34 thirds. On part A, B is the same kind of thing. Does that make sense there? Now, I don't want to say that like it's mad. Like I didn't really give a reason. Like why is it okay to cross multiply like that? That'd be a great question if you're wondering that. Because I encourage you to present math in a way that just follows truth. I didn't do that there. I kind of just said, hey, cross multiply, this works. That's different than saying, why is this true? So let's back up. I mean, sometimes you need things that are just quick and work well. But let's back up and give a reason. Why is that true? I can show you a reason really easily. If you just multiply both sides by the common denominator, now that's certainly okay to do. Let me stop there. Let me verify that what I'm doing we all agree is true. Because these things are equal, right? So if two things are equal and you do the same thing to both of them, meaning I'm multiplying 3 and 17 on both of them, if they were equal before and you treat them the same, they have to be equal afterwards, don't they? That's very reasonable, isn't it, right? Meaning this was equal to this before, and I'm treating them both the same, multiplying both sides by the same thing. That's called the property of equality. Again, I'm not going to quiz you on names. But that is you sense it, the truth of that, right? If two things are equal and you treat them the same, they're going to be equal afterwards. So this is certainly true, what I'm doing. Let me back up and show that the result of it, I'm proving that it will end up becoming cross-multiply. So I'm doing something that we all know is true. I hope I'm not confusing you. I'm not saying this is the way to do it. I'm verifying that our shortcut is valid. So I'm saying that's certainly okay. I'm doing the same thing to both sides. And then do you see what I could do? This would cancel, because it's over 1. This is over 1. The 3's would cancel. And over here, the 17's would cancel. So what? What do you have left? 2 times 17, which is exactly what I did when I cross-multiplied. And 3 times x, which is exactly what I did when I cross-multiplied. So all cross-multiply is common denominator legged out, basically. You see, it's true, isn't it? So anyway, that's just a demonstration that it's true. But I wouldn't do all that every time. Just do the shortcut. Zip, zip, and solve it, and it's the quickest way. Okay, so on number 10, in fact, I think I'll just give you a little more room here. Let me go 10a, what is it? 5 8s, 5 9s, 5 11s. 5 8s, 5 9s, 5 11s. And they want me to arrange in decreasing order. Arrange in decreasing order. Arrange in decreasing order. Now, on the next exam number 2 that we take, we got a while. It's not till the end of 25th of this month, though. This is March, isn't it? Anyway, so it's way off. But we will have, I'm going to give you like 3 or 4, not many, questions with no calculator. This would be one of the ones, no calculator, because it's good. You can do this without a calculator. And it's important that you understand, because if you had a calculator, you could just type all those in, right? Just get the decimals, whichever one's smallest, biggest, whatever it be. But I want to see that you can really reason out the fractions. So if you're wondering, I don't mean to make you nervous by that. If you're nervous, just look at the practice exam, which is already out there and available. You'll see what I mean. It's simple numbers. I'm not going to push you hard on numbers. I'm just going to give you things like this that reason out the fraction. Just 3 or 4 questions, and then the rest of the test, you can use a calculator. So anyway, so if I was to take, so what you really want to do with kids is really encourage them to be real with these fractions, right? I'm always talking about pi, but whatever, candy bar, whatever. So if you had a candy bar and you broke it into 8 pieces, let's see. So there's 4, 5, 6, 7, 8. Yeah, what if you took a candy bar and you broke it into 8 pieces and you said, I'm going to give you 5/8 of my candy bar. There's 5/8, right? A little more than half. And then down below, let me put that right down below. These are called fraction bars. I think they're literally called that. Even though I'm making them candy bars. So now I'm going to do 5/9. Now, 9 is a little more tricky. How am I going to break it into 9? Well, I'm going to have to do 5 and 4. 5 is 5 more than halfway or less than halfway? 5 out of 9. Is that more than half or less than half? More than half. This is the halfway point because that's 4 out of 8, right? So it's got to be a little past that, doesn't it? A little past that. And I'll just do 2, 3, 4, 5. So 5, 3. Wait. I blew it, huh? It's supposed to be 5 bars over there. So, well, try that again. So it's supposed to be 5. 2, 3, 4, 5. So 1, 2, 3, 4, 5. So 5, and then over here there's supposed to be 4. 1, 2, 3, 4. So there'd be 5/9. It has to be less, doesn't it? See how by drawing that diagram I know it's got to be? Because again, 5 had to be just past halfway, didn't it? And 4/8 is halfway. 5/9 is just a little more than half. So 5/9 is lower than 5/8. Or another way to put it, notice all the tops are 5, aren't they? All the tops are 5. So if somebody says, I'm going to take the candy bar and I'm going to cut it into 8 pieces. How big are those pieces right there? Now I'm going to cut the candy bar into 9 pieces. The pieces have got to get smaller, don't they? See how this piece here is smaller than one of the red pieces? because and then if you cut the candy bar into 11 pieces, they're even tinier, aren't they? And in all cases, you're giving somebody 5 of those pieces. So yeah, so we're really comparing 1/8, 1/9, and 1/11. That's really the deal, because the 5s on the top are all the same, aren't they? So 1/8 of the candy bar is bigger than 1/9 of the candy bar, and 1/11 is the smallest of all. So these things, the biggest one is 5/8, right? So they're already in decreasing order, aren't they? This is the biggest, this is the medium, and this is the smallest. 5/11, so the candy bar. Is that good? Is that making sense? Like you could do that without a calculator? Okay, good, all right. Arrange decreasing order. Okay, so let me order.
Yeah.
They're already from biggest to smallest?
Yeah.
Like the last one too, huh? The last one was already, it's kind of funny. All right, so tell me why. Who can? So do we think this one's bigger than that one, for example?
Yeah.
How do we know?
Because it's almost a complete whole.
This is almost a complete whole, isn't it? Yeah, good way to. That's almost the whole candy bar. So I'm going to give you 23 25ths of my candy bar. They only kept back 2 25ths, right? Yeah, and whereas this, how much? I mean, it's more than half,
More than
but
half, yeah, but it's not quite.
it's quite a bit shy of the whole thing, huh? You could just sense that, huh? Yeah, that's good. How about the fact that their tops are the same? Can you talk to me about reasoning from that direction? And maybe it's good to have a couple of good reasons. So the first one, yeah, I totally agree. It's almost a whole. And then how about the fact that when 2 fractions have the same tops and their bottoms are different, what does that mean?
Pieces get smaller.
What's that?
Pieces get smaller.
Pieces get smaller, yeah, well said. So if you cut the candy bar into 32 pieces, those are tinier pieces. And 25 pieces, those are bigger pieces, huh? So these are tinier pieces, so 23 of them is less than 23 of these bigger pieces, huh? Right, everybody understand? So the bottom number, is the candy bar is cut into 25 pieces. If you take one whole candy bar and cut it into 25 pieces versus if you cut the candy bar into 32 pieces, they're tinier, aren't they? When you cut it into more pieces, then they're tinier. They're tinier. 32 pieces. Okay. Right. So these are tinier pieces. So this one's got to be smaller. This one's got to be bigger. We agree for 2 different ways of logically reasoning. And then what about the 1/5? You guys think the 1/5 is the smallest?
Yeah.
How do you know?
It's below the halfway mark.
Yeah, we just kind of
No.
judged it by like the halfway mark. So we knew that 23
Good.
over 32 was more than half, but 1/5 is less than half.
Yeah. Yeah, this is less than half, clearly. These are both more than half, clearly. Yeah. Or you could do common denominator, huh? Multiply top and bottom by 5. That's 5 25ths, isn't it? And this is 23 25ths, clearly bigger. Yeah. So this one is the smallest. So yeah, they actually are in right order, aren't they? That's the smallest. Does that make sense? Feel like you could do that? And that kind of thinking is what you want to give to students. So the fractions are real to them. Math is so much easier when it's real. I mean, that really is. If somebody was after 25 years of teaching math, somebody's just to stop me and say, what is it in a person that makes them a math person or makes them seem to know what to do in math, especially in word problems? I would say over my years of working with lots of students, the more it's real to somebody, the more when they look at fractions or whatever the word problem is, they're thinking about real life things instead of just numbers on a page, then they do better. So the more real math can become, the better. It's easier and it's more enjoyable as well. Okay, I want to jump in particular to and you I'm sure you'll remember for adding, subtracting, you got to get common denominators, all that. I want to jump in particular. Oh, well, I guess we just do the same thing there, huh? Yeah. Okay, it's not that big a deal. Anyway, let's do it. So I'm going to go to 15 part E, 1/6 minus 2 5/8. So 15 E, 1/6 minus 2 5/8. Right. Okay, so let's do that one. How do you subtract when you've got like a regular fraction and then a mixed number? How are we going to do that?
You would start by turning the mixed number into an improper fraction.
That's one good way. That's really a good idea. Yeah, so do you remember, how do you take this mixed number and make it like a normal fraction?
Is it 8 times 2 plus 5?
Good. Good, exactly. You multiply the number in the bottom and you add the one in the top. Exactly. 2 times 8, add 5, so that'd be what? 16 plus 5, 21. And then, so is it just 21? It's 21 what? 8. The denominator stays the same, huh? Good so far? Do you remember that?
Yeah.
Okay, so, oh, by the way, again, I don't want you to leave no stone unturned. Why? Why is that true? Why do you multiply the bottom and add the top? Do you know a good reason?
Because you're undoing what they did to make it a mixed number, because you just took out 2 whole 8s.
Mm-hmm.
So by multiplying it back, you're just undoing what they did to make it a mixed number.
Oh, nice. Yeah, good. 2 whole 8s. Yeah, in fact, we could show exactly what you're saying like this. Because 2 and 5/8 means 2 plus 5/8, doesn't it? If you said, I've got 2 and 5/8 candy bars, I got 2 plus I got 5/8. And then how would you add those? You'd put this over 1, because that's the same thing, right? And then you'd do what to add those? You would have to get a common denominator, so you would multiply top and bottom by 8, wouldn't you? So think about what you're doing. 2 times 8, add 5. 2 times 8, add 5. That's all it is. That rule is just a shorthand way of showing what we would do longhand. Yeah, so great. So you multiply the bottom number, add the top. Now, what do we do at this point to subtract these guys? Common denominator. You could make it 48, but there's a smaller one, huh? Yeah, you could just make it 24. It'd work with either one. You don't have to do the lowest common denominator. You could do 48, but it's just easier if you do the lowest. So top and bottom by 4, top and bottom by 3. Why do we do top and bottom?
Because it's like you're multiplying by 1.
Yeah, because you're multiplying by 1. You're not changing anything, huh? You're not changing anything. So nothing is changing there. I'm doing same thing top and bottom, so nothing is really changing. So it just makes the fraction look different. What is this from 63? Without being different. So now we can subtract them now that they have common denominators. So it's minus, was that 59? Over 24. Now we have to change it back. I think they want mixed number answer in the end. Pretty sure. So how do we change that back?
You would divide 59 by 24 to see how many whole 24s go into.
Exactly. Just like, so it's exactly the opposite. When you have mixed number, you multiply. So to go back to mixed number, you divide. I'm going to leave the negative out. I know it's negative something. So yeah, you just long divide. 24 into 59 2 times. 48, remainder 11. So it's 2 and what? 11 24ths. It's the bottom over the left. All right, that